Hi, my name is Josh, and I watch the FCC approval database so you don't have to. Today, we're going to do a virtual teardown of the Yell and Jordan LLC Stunt Stand sensor. So, hang in there and we'll get to that in just a second. What is this that we're doing? Every product that's sold in the United States that contains a radio has to go through an FCC approval process. As part of that process, they send it off to a testing lab, which measures it for radio interference and all of that good stuff. They also submit the schematics, the block diagrams, all of these pictures of the exterior, the interior, the manual, etc., to the FCC. As part of that application process, it all gets published online, and what we do is we look at those documents to do virtual teardowns of the device. Usually we don't get schematics or block diagrams. Those are considered quote-unquote trade secret or proprietary, but we do get the interior photos an awful lot of the time, and that's what we're going to look at today. So I watched this site called fccid.io, and today this Stunt Stand sensor popped up in the feed, and I was like, what is that? So went ahead and pulled it up over on the FCC site, and it's got a whole bunch of stuff. There's a manual. So if we look at the manual real quick, it's not super helpful. One separate complete bridge weighing sensors are placed on the four corners. Like differential are there, So EEPROM for the storage calibration. So, it's mostly specification more than anything else. So, let's just look at the guts of the thing. So, this is how those start, which is kind of weird. But here we can see inside the device. Up front we see we've got this micro USB, a LED, another LED, and a switch. So probably a power switch. If we open it up, there's a little LiPo battery here. Then there's a bunch of wires going down to the bottom here. And we know that it's got four sensors in it. There's 1, 2, 3, 4 of these little screws. So, there's 4 of these connectors going off. So these are probably the sensors. As we look at the circuit board, the antenna jumps out at us. So this is the little Bluetooth antenna. And then let's go have a look a little bit further down. So this is the actual main PCB. If we look at it closely, we've got these 4 sensors again coming in here. We've got this stuff up here, and these are the 2 battery terminals here. We've got this stuff along the side. This is our micro USB connector, which means that this is one of the LEDs. This is the other LED, and that's our switch. Down over here, we've got, this looks like a power supply of some sort. There's this little SOIC 8 here, and then there's our main microcontroller. If we look more closely at the input sensor lines, actually here, let's start over here. Start where the power comes in. So this is our USB connector. Half of it comes off to here, and half of it goes off over there. So this is our power for charging up the battery pack. This side is ground because that is tied in. This side is hot. Comes off over here, runs up and under somewhere. Can you see that on the top view? Sorry, here's the flip side of that board. So there's that stitching, comes out and into 2 sets of things up here. So if we go and look there, we've got here and here are those 2 pairs of vias. You're just going to take my word on that one, sorry. So this looks like what's happening is the input power from there is coming off into here on this chip, which is then sending the power across to here to charge the battery. So this is probably the battery charging circuit. If we look closely and squint and hold your tongue at the right angle and maybe turn your laptop, you can see 4056. With a little bit of Googling, we find the TP4056 1 amp standalone linear lithium ion battery charger. And if we look, here's its pinout. Here's our battery terminal. Right across from it is our input terminal. We've got charging and standby. We've got ground. We've got a programming resistor, and then a temperature sensor. Or temperature cutout, I'm actually not sure which it is. So, if we go back to our boards, we will find, got our input going across to the battery, so that matches. we have this thing here, which will tie down to ground. We've got this is our programming resistor. And then over here, we've got our two indicators of charging and standby. They're active low. And if we look at where these go, we've got those coming across. So it's across from here on the board. We need to get some bearings, because we've got to flip it over. So across from there. And that's about it. It's kind of in the line with that via there. So here's that via. And here's this. So boop, boop. Here's those two pins. And they come across, sneak out and around this LED, and then to here and there. So this diode is a bicolor LED that can be either red or green, probably, depending on which of the pins is powered. So it's got this center pin, which is tied to VCC, or actually to the input from our charging circuit to these two pins. So when this thing is charging, it pulls one side low, this will go low, power will run through, and that LED will turn one color. When it's in standby, the other one will go, which is probably that everything is charged and it's just maintaining. So that's how, or rather, that's what this piece up here is. This is our power management circuit for the battery side. Then if we look, we get this positive out. Here's our power switch. When we turn it on, we're going to connect to this big old plane here. And we see that on this side, it comes across to a missing SOT23. This is an oddball one. I think this is a transistor probably to connect power if the power goes low, but I'm really not sure. It might be a diode too, but it's a weird one. Could be a 2-diode package to do flyback. But this comes down to here to a little power regulator, and it's a switch mode. So the power is coming in here, going out there and across, and yada yada. So this is just our power management circuit for the actual circuit side, our voltage regulator, which flows down and into here, where we find our MCU. If we scroll down, we get a really nice picture of it. So this is, and they helpfully labeled the antenna in case you missed it. So this is our microcontroller for this thing. This is, a little bit of Googling, a Cypress CYBL 10x6x system on chip. This is actually pretty neat. It's got a little Cortex M0. It's got built-in BLE. It's got a bunch of ADCs and so on and so forth. And if we go down to page 14, we can find the typical applications diagram. So this looks to be the same pinout that we've got there, which is kind of handy. So we can see that our antenna right here should stick out like a sore thumb, and it does. So they're even in the same orientation in these two pictures, which is handy. So we'll expect to find a 24 megahertz clock here and a 32 kilohertz, 32 kilohertz crystal clock up there. And, wrong way. Sure enough, antenna up 32 kilohertz, down 24 megahertz. So this is probably the exact pinout that we're using without doing any further cross-reference. So from there, we know what this thing is, which is cool. We can figure out kind of how that hangs together. Let's go back and look at the actual sensors now, because we've got these 4 connectors around the edge. If we zoom in here, you might be able to read this, LM358. That is the LM358, which is a dual op amp. So in here, we've got 2 op amps on either side coming in and going out towards pin 1. If we go back and look at our circuit board, this side is easier to see. So we've got this left front sensor. It's got 4 pins. These two are pretty much in parallel, right? Like they're very similar structures all the way across. They come in to right here and to right there, and then come out here across to there. So this is another differential probe of some sort. Since we think it's got strain gauges in it, these are probably weight sensors. So we've got 2 of these 358s. We've got 4 channels, so that matches. 2 channels here, 2 channels there. And all of these nice big fat low impedance traces come down into our microcontroller for measurement. That leaves the only little subsystem that we don't know about as this little chip over here. This one was kind of a pain in the butt to figure out, but I thought it would have an EEPROM. And if you just go and blindly search for I2 EEPROM pinouts, you'll find things like this because they're old school. But on one side, on pin one side, we've got our address and ground. On the other side, we've got our serial lines, write protect, and VDD. On SPI EEPROMs, all of your signaling is over here as well. And if we go over here, this thing has, so this is pin 1. This is to ground probably, and then these are going to be the address pins. And if we look, this is those on the other side, and all going to ground, which makes sense. Then we have these other traces coming over towards our microcontroller. And if we go up here, you got zoop zoop there. These would be the pull-up resistors on I2C. Then those go off and across and under over to here. And if we do the cross-referencing, we'll find that they do go to P0.4 and another one, which are the I2C, or sorry, yeah, the I2C bus for this micro. So this is our I2C EEPROM. So at that point, we kind of know how this thing works. It's got 4 strain gauges that feed into this micro. It gets some calibration data or something from over here. And then the data goes out over BLE, which that's, you know, not a bad 15-20 minutes work. The next question, though, is what does it actually do? So I assume that it's a stunt stand for like bikes or motorcycles or something like that because I'm from the Midwest. I went and Googled it, though, and it turns out that the stunt stands are for cheerleaders. Because when you're doing this sort of a, you know, standing up structure, like the pyramid thing, I hate carousels. So when you do pyramids like this, you've got to have good balance on the floor and up top. And so what these are is they've got this virtual foot thing that lets you train your team to hold it up. And then they've also got these bases so that the people on top can practice learning how to balance on top of a platform. And if we look down here, this is the thing that we're looking at. We've got a really, like, it's a pretty nice prototype, sort of. The chassis is not so perfect, but, you know, it is what it is. That they say expected by Christmas, also guaranteed by Christmas. It's December 2nd, and they've just gotten the FCC approval going through. So I don't know if it's actually going to ship before Christmas, but I hope it does because it's a neat thing. Anyway, so that's what this is. This is a stunt stand. So that's taking this thing apart. Figured it might be interesting to talk about strain gauges a little bit more if people are interested, but that's kind of the end of the teardown of this particular product. So hang around if you want to hear a bit more about strain gauges. Otherwise, thanks for watching. Leave any questions or comments down below, and if you see something down there that you can answer, please do so. Thanks. Okay, so strain gauges. Strain gauge is just this printed circuit on a substrate. And you connect wires to here, and then you measure the resistance along those wires very, very precisely. And the resistance of a wire goes up as the wire gets longer, and it goes up as the wire gets skinnier, right? So if you make a wire fatter, resistance goes down. Or if you make it shorter, the resistance goes down. Well, if we start with a foil pattern like this, so let's say that we make a circuit board just like that, with very, very tiny traces, then whenever we bend it along the length of it like this, so if we push up in the middle here to bend it out, to bow it out, these things have to get longer, and they also get skinnier because that's, you know, they're just stretching out. As they stretch out, they get longer and skinnier. When they get longer, the resistance goes up. When they get skinnier, the resistance goes up. So you get a pretty, relatively, I guess, marked increase in resistance in this case. On the other hand, if you push down on it to bow it in, you get things that are shorter, and because they're shorter but the same volume, they are fatter. So the resistance goes down in that case. Now, the relative change here is pretty small, but with a bit of compensation and a bit of careful design, you can use a Wheatstone bridge to measure that resistance. And the way that we usually do that is by measuring the voltage drop across it. So with a little bit of work, you can measure the strain on this piece of substrate, probably metal, to see how much weight is on it. And I think over in our device here, that's what these screws are for. I'm betting that these are probably things that you tighten up in the factory to zero out the initial strain, to get everything to zero when there's no weight on it. But I might be wrong. Anyway, so that's how strain gauges work. Thanks for sticking around through this longer bit. If you have any questions or comments, please leave them down below. I'll include links to just about everything here down in the doobly-doo. Cool, thanks. Bye.